moles per unit time expands in the same way. So Fa is Fa0, 1 minus Xa. Because it's the same thing. Either the moles are sitting in one place or the moles are moving. They still relate to X in the same way. So if I rewrite this, I have minus Na0 dxa dt is equal to Fa0, 1 minus X in, minus Fa0, 1 minus X out, plus RAV. I need some space. It's over. Okay, so notice the ones cancel here, and this is Fa0, so I have minus Na0 dxa dt is equal to Fa0 X out minus X in plus RAV. And this is the unsteady equation for a CSTR. If we specialize it to steady state, then the time derivative is 0. At steady state, the time derivative is 0. And I can separate things out. Well, actually, before I separate things out, I might want to rewrite something. Yeah. Make sure I haven't screwed up the units here. Actually, before I go to steady state, I do want to manipulate this a bit. I'm going to divide through by the volume. So let's divide through by the volume. And I'm going to divide through by CA0. I'm going to multiply and divide by CA0. I'm doing that for a reason, because I want to introduce tau here. That's a 1 over tau. So I can rewrite this as minus Na0 over V dxa dt is equal to Ca0 over tau, X out minus X in, plus RA. And that's another form of the unsteady equation where I just introduced tau 0. Now what I'd like to do is go to the steady state version. At steady state, I set the time derivative to 0. And what I'm left with is the following equation, which is tau 0 is equal to. So what I do is I move this to the other side of the equation, and I divide by RA and multiply by tau 0. So it's Ca0, X out, minus Xa in, divided by minus RA. And this is the general equation. And the general equation, again, what does this suggest? This suggests that I plot 1 over minus RA versus Xa. And again, when I plot minus 1 of RA versus Xa, as I did over there, I expect the curve to go up. And what does this say geometrically? I am not, so here I have Xa in, and here I have Xa out. I am not taking the integral under the curve here. What I'm doing is I'm taking, and also I need to be careful here. This is, before I go on, I need to be careful where RA is. Where is RA evaluated? And what concentration is RA evaluated? Where is the what concentration is the reaction taking place? At the outlet concentration. So this is minus RA out. Okay, so notice what I have here. I have minus 1 over RA, not as a variable, but evaluated at the outlet, here. So it's the height of the curve at the outlet conversion, times XA out minus XA in. That's this width. What shape do I get if I multiply a height by a width? What am I getting? Huh? Who was I up to? Was up to you? Right. I get the area of a rectangle. So what I'm getting is the area of the rectangle whose height is the height of the curve at the right endpoint. And that is equal to tau 0 over CA 0. So my performance measure, when I guess the only thing that would have the units of time is in fact what comes out. And that's why I did this manipulation. My performance measure is tau over CA 0. And again, let's look at the special cases for CSTR. Are there any questions?
When you graph is a conversion of 1 over minus array, does that mean that there's a product, it's as if there's a product of conversion that's already at the input, when you graph it?
No, wait a second. I can graph anything I like. I'm making a curve. This curve is on plotting the rate function. All rate comes from kinetics. I can always plot that. I don't prejudice anything by making a plot. And then I look at the formula and I said, what does the formula say about this plot? The formula says tau over CA, tau naught over CA0 is a width, x out minus x in, times the height of the curve at the right endpoint. The height of the curve at the right endpoint.
But what's the physical meaning of the rest of the curve?
It's the kinetics. It's not relevant for this calculation, but it's there because of the kinetics. I can always plot the
It has
kinetics.
nothing to do with what's happening in the reactor.
Correct, exactly. The reactor, everything happening in the reactor is at RA out. And that's why I use the height of the curve, not just
So
here, but all the way across.
So it's the only point that has a physical meaning
For the CSTR is that point, right, exactly.
So, why is that approximation of the performance relevant when the other cases the area that you factored was figured out of the curve?
That was a different case. That was the batch reactor. Different reactor. This is a flow reactor.
Here you overshoot because you get an area that's above the curve. So
That's okay. Remember, I'm working from the formula. And the graph is representation of the formula. I derive the formula. And this tells me that when the curve goes up to the right, then the area is bigger than the area under the curve. If the curve went down, if the curve looked like this, then the area at the right endpoint would be less than the curve. And if the curve were more complicated, then who knows what I get? It could be less, it could be more. All depends on the shape of the curve. I drew you a curve of an nth order reaction. But as we know, not every reaction is nth order. Sometimes it's more complicated. So whether it's more or less depends on the shape of the curve. And there could be many shapes to the curve. I just drew a simple shape for an nth order reaction, where n is positive. Okay? Let's do the special cases. Special cases, again, I'm going to run out of space. I wanted to keep this on the blackboard. Special cases. So if I go to constant density, I don't have to do much. CA times 1 minus XA, CA0 1 minus XA is CA at constant density. So this becomes CA in minus CA out. Because just like here, the ones will cancel. So constant density, I have tau 0 is equal to CA in minus CA out over minus RA out. And in that case, again, I plot minus 1 over RA versus CA. Of course, I erased that. And that curve typically goes like this. Here I have in, out. And again, this tells me I use a rectangle. The width, CA in minus CA out, and the height at the outlet, the height at the left end. And that area is tau 0 over CA 0. So as Stephanie pointed out, the only point on the curve that has any relevance is the outlet, because the concentration everywhere is the concentration at the outlet. So everything's evaluated. Linear volume expansion. Linear volume expansion, I just, where am I? Well, what changes? The only thing that changes is, I mean, the curve looks the same in linear volume. This looks the same. In linear volume expansion, it's just RA depends on the concentrations, which depend on the volume. So there's nothing, the curve looks, the formula looks the same for linear volume expansion. Anything else I want to say about that? I can't hear you. Can I repeat what? Yeah. No. Do you see an integral here? Yes. Do you see an integral here? So there's no area under the curve. It's an area of a rectangle. Oh, I'm sorry. Thank you. It's just tau naught. It's not tau naught over CA0. You kept saying area under the curve. The area of the rectangle is just tau naught. There's no CA naught. It's minus that. Thank you. Okay. Now, I'm going to derive all the performance equations, and next time I will do examples. But this way I want to get all the performance equations. Okay, so let's now look at the, are there any other questions on the CSTR? Any questions on the CSTR? Okay, let's look at the plug flow reactor. The plug flow reactor, if you remember, the concentration varied continuously. So if I apply the concentration versus position, there was a continuous variation. Unlike the CSTR, where the concentration was the same everywhere. So CA is a function of Z. And if I have an unsteady case, it's a function of T as well. So if I'm going to do a balance, I have to do a differential balance. On a little dz, the cross-sectional area is, say, script A, dz, which I'm going to call dv. So I have to do a balance on dv, where this is z and this is dz. So I need to apply this expression here. The accumulation is the in minus out plus the rate of generation to that little dv. Is that clear what I'm going to do here? Everyone understand what we're going to do? We're going to do a balance, a mass balance on this delta v, this dv, and then we'll integrate it over the whole reactor. Okay, so what is the rate in? So again, I have CA is a function of Z, and FA is a function of Z, and maybe T. So what is the rate in? I think I was up to you.
Yes.
The rate, the moles per unit time of A entering this little dV.
FN? F, F,
FA. No, FA in is at the inlet.
Right.
I don't want into the reactor, I want into this dV.
FAN at some point.
No, FA in is the inlet to the reactor. What is coming into this little dV?
FA as a function of Z.
FA of Z, good. And what is leaving this reactor, back to the back? When your hand's in front of your mouth, I can't hear a word you're saying.
That is FARCO.
Out is over here. I want coming out of this. Yellow? No, the guy, the lake people. Sleeping.
I don't think so.
The same thing's coming in as coming out?
FA of Z plus DC.
FA of Z plus DC. How about the rate of production of A in this small regime? RA times RA times dV. RA times dV. Okay, now the only thing missing is the left-hand side. The time rate of change, the accumulation of moles of A in dV. What are the moles of A in dV? Now I'm using the partial derivative because I have dependence on Z as well. So I mean partial with respect to T. On the left, I want the time rate of change of the moles of A in this little dV. How do I represent the moles of A in this dV? Remember, dV is tiny, so what are the moles of A in dV? I'm sorry? How about someone raising their hand?
NADV?
What are the units of NADV? That's moles times volume. That's not it. What are the units of that? You want moles. We've got time. You're giving me moles times area. That's the wrong units. CA. CA is moles per unit volume. CADV. Okay, why can I do that? Remember, I said, you got to be careful. You've got a volume inside the derivative, volume outside the derivative. Why can I do that? I can do that there are two important reasons. First of all, this is a flow system, and this is a physical volume. It's not a volume of fluid, it's a volume of reactor. The reactor doesn't change. That volume of reactor doesn't change. So this is a physical quantity dV that's hardware. It's not gas. Moreover, since it's infinitesimally thin, we're going to let it go to zero. Even if the concentration varies over the reactor, it doesn't vary over an infinitesimal distance. And that's the assumption that CA is continuous, if you remember from the calculus class. If you assume CA is continuous, then as the delta Z goes to zero, CA doesn't change. So that's why I can do this. And dV comes out of the derivative because dV is just a physical constant. It's a physical piece of reactor. It's not like this where it's a volume of reaction mixture that can change, expand and contract. Here it's a physical volume of the reactor. Okay, so now I can divide through by dV. Well, so I can divide through by dV. Delta V. be consistent, I should make these delta v's. And I could think of, if this is z, then script a times z is v. So I could make this v and v plus dv. The delta v's cancel. And I take the limit as delta v goes to 0. Yes?
How do you take it from V to V? I didn't get that.
V is AD, dv is AdZ. So z is AD, v is,
Okay.
v of z is the volume from here to z. If I define it that way, then this is just equal to A times z. As opposed to the volume of the reactor. So that way it sort of simplifies the notation a bit. So what am I left with? I'm left with dCA dt is equal to RA. And what is this? What is the limit as delta V goes to 0 of FA of V minus FA of V plus delta V over delta V? Who was next? I was up to somebody. Did I ask you already? Stephanie? What kind of derivative and with respect to what? Okay, what kind of derivative? Partial derivative. And is it plus or minus?
It's minus.
Minus. So it's minus df dv. So this is the unsteady equation for the plug flow reactor. Okay, so let's now go to the steady state version. Well, actually, let's put in XA. So again, I'm going to, well, actually, let's go to the steady state version. Let's go to the steady state. So what happens at steady state? At steady state, the left-hand side is 0. So therefore, I get dFA at steady state. The ddt is 0, and this becomes a total derivative. So I have dFA over RA is equal to dV. FA is FA01 minus XA. So dFA is FA0 minus dXA. So I have FA0 dXA or minus RA is equal to dV. And now I integrate this equation. If I integrate it from z equals 0 to z equals L, length of the reactor. I want to finish the sentence first. Let me finish the sentence first. So here I get the volume of the reactor, total volume of the reactor. And what I have now is the volume, so I have the integral dxa over minus RA. dxa over minus RA is V over FA0. And this goes from XA of 0 to XA, XA in to XA out. And if you like, you can multiply both sides by CA0. And you get CA0, the integral XA in to XA out, dXA over minus RA is equal to CA0V over FA0, which is tau 0. question?
Yeah, where's that minus sign come from? Because from the,
This minus sign?
Yeah.
I'll tell you. DFA is minus FA0 DXA. Minus FA0 DXA. This minus sign came from the DFA, which has a minus sign in it. Okay, so notice I have CA0, the integral from XA into XA out, dXA over minus RA is equal to tau 0. I want to plot that. Well, luckily, I don't have a lot of space on the blackboard, so I'm going to have to use some of the plots I've made before. This says I should plot minus 1 over RA versus XA. Well, luckily, I just did that. I plotted minus 1 over RA versus XA. For a plug flow reactor, the integral of the area under the curve, the integral from XA into XA out, is tau 0 over CA0. So for a plug flow reactor, the area under the curve from here to here is tau over CA0 for a plug. Whereas the area of the rectangle was tau over CA0 for a CSTR. Is that clear? For a CSTR, I had tau was CA0, x out minus x in over minus RA0, the area of this rectangle. Here, tau is CA0 times the area under the curve. It's the same figure. So notice if the curve increases like this, like a simple nth order reaction, tau 0 for the plug is better, smaller than tau 0 for the CSTR. The curve looks different, that might not be the case. Let's look at the special cases. Special case. Constant density. Constant density, CA0 dXA, at constant density, CA is CA0, 1 minus XA. dCA is minus CA0 dXA. So at constant density, CA0 dXA is just minus dCA. So I could replace this by dCA, and I have to flip the limits because of the minus sign. So I get dCA over minus RA, tau 0. CA out to CA in, where I use the minus sign to flip the limits. Well, luckily, since I don't have a lot of time, I can't make new graphs. So I have to make use of this old graph. Here I had tau 0 was CA in minus CA out over minus RA, the area of a rectangle. Now I have tau 0 is the area under the curve of minus 1 over RA. Same plot, but for the plug, I now have this area. Tau 0 for a plug. Again, the same curve. One is the area under the curve, the other is the area of a rectangle. This will go back to your question eventually. And finally, linear volume expansion. Well, for linear volume expansion, the expression doesn't really change. I just have to remember that RA depends on CA, which depends on the linear volume expansion. Are there any questions on that? Okay, so these are the basic equations and these are the performance equations for the three basic types of ideal reactions. Batch, CSTR, plug. And we've specialized them to steady state for the CSTR and the plug flow reactors. We're going to start the next hour doing examples. Okay, so I'm going to do a number of examples, and I will also give you a summary sheet of all these pictures and all these formulas.
Are we still gonna have reciprocation to the other one?
Okay, so let me tell you what's going on as far as today's concerned.